Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. So let's go ahead and get started for the next session. So this session is on code and program modeling, and we're happy to have kind of two speakers. One who's coming more from a PL software engineering perspective, and then another one who's coming more from a machine learning perspective. So the first speaker is going to be Earl Barr. So he's a rare bird in the sense that he's been working both in the programming language and the software engineering communities. And this is something from the outside I didn't realize, that it's actually unusual to be able to do work that's considered significant in both communities. Earl was one of the, was kind of involved in the kind of early days of the naturalness research. So he was on the original, some of the original papers on that. And he and I have also had a kind of very fruitful collaboration about applying n-gram language models. And one thing is that I noticed was kind of also very impressive is that when I went through his publications list, there seemed to be no fewer than 5 Best Paper Awards in the past 10 years, which is very nice. So thank you, Earl.
Thanks, Charles. The brief that I was given by Charles and Tien for this was to tell the ML and NLP people in the room about problems that might be particularly interesting to you, areas that where your techniques and approaches might be particularly fruitful. I'm based in London, and it's 10:30 at night for me, and I've gotten about 4 hours of sleep for the last 2 nights. So I feel like I'm underwater right now. So given that I've cast this talk toward the ML guys, fellow software engineers, help me out. If I have a brain freeze, help me explain these slides. Okay. So a core seminal problem in software engineering is inferring intent. Because intent is more fundamental than semantics. If we know what the intent is, we can constrain and trap the semantics problem. And so hidden behind a blizzard of terminology that you've been exposed to in the talks today and yesterday, and in your forays into the software engineering literature, is a search for intent. So when in the beginning of a project, ideally you have requirements and you have a code base. And so the traceability problem, which you've heard a lot about in pieces today, Jane and Dennis, is finding this linking the requirements to the code base. And here's a particular example. Class implements requirements 1, 2, and 3. So that's some class here in the code base. And the reason this problem is so important is because when we have knowledge of the requirements, we can know things like what some code is intended to do. And if we know what it's intended to do, we can build tools to check whether it in fact does that. We can try to verify, which is a holy grail of software engineering. Verification, validation of the correctness of a program. So, and it can also prioritize development and which bugs to fix. It's well known that most large projects have thousands or even tens of thousands of open, unfixed bugs. And what that means is that's because of finite resources. We have finite resources to fix bugs, and so we need to allocate those finite resources efficiently, effectively. And if we knew which requirements were bound to which bugs, we could make those decisions more effectively. And requirements constrain the space of code invariants and properties. When we know code invariants, when we know properties of the code, we can check whether they hold or not. And they're useful for these tasks, code understanding and verification, and others. Am I missing software engineers? Am I missing an important one here?
Traceability.
Sorry?
As relating to traceability.
as related to traceability for this edge here? Good?
I mean, there's all sorts of other things, but I'll talk a little bit about that when it's my talk, but about safety analysis and compliance verification and all
I hope you will jump into this talk if it becomes, if you see a point where where it's better, makes more sense. Okay. So a code base is, I oversimplified a moment ago, a code base is a test suite and application code. And I've written the test suite here on the requirements side because often a test suite is informed by the requirements. It captures some under approximation of them. And I note that although I haven't made a link here, even this link between a test suite and the code base is problematic. We often don't know for a given test case what it's intended to test, what it's supposed to test. So, and you might think that if you're the ML people might think that that's strange, or maybe some of you might. It's immediate why it's not strange, but you might think, oh, I just look at the path. But if you look at a test case that is testing the Windows code base, for instance, say you have a test case that's testing the key integrity of a database. It needs to traverse the file system of the operating system. It has to check, or it traverses the code that opens files and closes files in the operating system. It's not intending to test those, but it needs to traverse them in order to get to the point to test the database system. And so knowing which pieces, which subparts of the path that it traverses that it is intended to test, is non-trivial. And a code base is just a checkout. It's just a snapshot of a version history. And this conglomeration here is a software repository, as in mining software repositories in the MSR sense, aka the salt mines, where we software engineers, when we're doing mining, this is where we go and chip away at the features and properties in order to correlate features of this data with software engineering outcomes of interest. But these things don't just happen in a vacuum. Requirements come from somewhere, and the source is stakeholders. And traceability includes this edge as well. It's this. These are called pre-requirements and post. And according to Finkelstein et al., more problems in projects happen here primordially. And it'd be really great, again, if we could infer this edge. All of these relations are problematic. Our requirements are partial, and the links between our requirements and our different artifacts are partial and noisy. And it's more complicated than that. We have all of this additional data. We have issue trackers, mailing lists, documentation, and logs. And we've been talking about that today and yesterday. So Razwan, you worked on this link. You were using information retrieval to connect issue trackers with the code base here. Not with the version history, because you weren't looking at commits, but you were looking at files inside the current checked out version. Did I understand that correctly?
Actually, for every bug report, we created a snapshot of the source code that was in place when the bug was submitted.
Oh, so you were making the connection to the version history then?
Yes.
Yeah. So Chris, who's into his laptop right now, he did a lot of work right here on inferring this arc. And also this arc. Help me out. Who else is particularly has focused on particular arcs here? Yeah, Nagapan here. Tao Xie has been everywhere. What were you going to say, Jane?
I was saying a lot of the work of going to documentation, I think, that Andy did, right, with Julio and Jonathan Miletic.
Yeah. And also on documentation, Martin Rubia and Peter Rigby are currently doing things here. So then mining software repositories has evolved from this core to, has been expanding because we're data hungry, just as machine learning is data hungry. We're trying to gather more data that we can leverage to solve our problems. And again, I want to emphasize, this is all noisy data. We're missing edges. The edges that we infer and that we have documented are erroneous. And mining includes requirement documents when we have them. And it even includes stakeholders. There was at ICSI, I forget when, we put some developers into an MRI machine and gave them some problems. Which one was that, Prem? Which ICSI was that? Was that 2014?
14.
That was 2014.
2014.
Yeah.
2014, yeah.
So what this talk about, I didn't realize this until earlier today, but this talk is about the fact that Jane and Dennis's work on TraceLab, they need your help. They need, because I think, Jane, there are lots of open problems here still. There's lots of different tools, and although you've brought a lot of weaponry to bear, there's more to be done here, and there's more that needs to be done. And so yeah, so let's help her out. Let's help out TraceLab.
He's on the project too.
Oh,
Yeah.
Colin. Okay. I didn't connect that you were an integral member also.
Yeah.
Okay. So this is where I'm going out on a limb. I'm suggesting maybe a related an ML technique or tool that might be useful here, relation extraction. So as I understand it, this extracts entities and their relations from unstructured text. So this is where Dana, I don't see Dana, there you are, where your work comes into play. And where, I hope that this picture that I've shown could give you asked, where could this be useful? Well, you can recover these links. And when you recover these links, you can give us features that we can use to build tools that can check whether they hold or not. So, and the other thing that the other point I want to make that why this might be particularly interesting to the machine learning NLP community is that all of this data is relatively structured. Source code is structured. Requirement documents are usually in semi-formal English, some kind of sub-dialect of English, or they can even be formal, or they can be some mix of formal, semi-structured and notes on the back of a napkin, but they're more structured than just text on the web, arbitrary text on the web, and that structure and those constraints might simplify the problem, might be able to be leveraged to improve the performance on some dimension, like in terms of the accuracy, its resistance to noise, or speed. Okay. So the problem that we software engineers have is that much as requirements are great and we would like to have them, we often don't have them. Many projects simply, we don't have requirements at all. I worked on Wall Street, and I worked for a startup, and we didn't do requirements at all. Everything was verbal, and it was all about meeting deadlines. It was a very ad hoc development model. And I think the dirty secret of industry is, even given the agile rage right now, it's mostly ad hoc. And so we don't really have requirements. And if it were easier to, I think if it were easier to maintain, to discover and maintain these links, it would make it cheaper and also more worthwhile to save this data. Yeah, Jane?
So I'd just like to make one comment there, because I think in software engineering projects, they tend to often not have requirements. But when you get into the systems engineering world, they almost always have requirements written down. So it's kind of the two sides of it.
So Jane just talked about a domain that I'm not familiar with, where I didn't work. But that's also interesting. That means that there are some domains where you can rely on this existing, and others where it is a problem. It has to be discovered. When this doesn't exist, what we can do is we can think about another way of recording and capturing programmer intent, which is programming by contract. And in this case, we don't have the requirements written in a form where stakeholders can understand them necessarily. We have them in a much lower level in the form of specifications embedded in the code. So this is a little fragment of a language that I admire called Daphne, here from Microsoft Research Redmond, a language that supports design by contract. Note the TM there. Yeah. And so this is a precondition. This is a precondition that says this function expects this to hold on that parameter. And this is the postcondition, which says that the guarantee is that this will hold on X when it computes. And
your slide of your lamentations about the absence of requirements. Is this becoming more of a problem or less of a problem as people are doing this kind of agile DevOps kind of stuff?
So there's it is true that agile means that there's requirements manifest in the agile model as story points, and they are being written down, but they're written down in a very vague, very terse, almost slogan style way. Almost as like labeling for a collection of, I'm having a brain fade on the word, in a movie when they have a storyboard, like almost in a storyboard style. So they're even less useful, to my mind, than semi-formal English requirements in a DARPA. Abram?
In the DevOps context, there's a lot of these files kicking around, requirements.txt, and a lot of the times they really should be renamed to dependencies. But oftentimes they're basically how to build the system that's going to host your software. So in a DevOps context, requirements is oftentimes how to build the environment.
For the uninitiated, could you tell us what DevOps means?
DevOps is when you ask your programmer to be a sysadmin at the same time and basically deploy to the cloud for the most part.
So DevOps is also sometimes continuous deployment. So basically when you have a build infrastructure that's set up so that way after every commit, you have really good automated tests and you're always running the latest version. So GitHub is very well known for doing this. So they say, we don't have releases, we don't have a deploy button, we have commits. And basically after every single commit that's done to their code base, it's up there running on the site.
And the etymology is DevOps is developer operator, something like system operator, but in between. You might still have a system in. Sorry.
No. So the cool thing about design by contract is that you can, if the program is fully annotated with these annotations, you can mechanically verify it. You can prove properties of it. The fly in the ointment here is loop invariants. Loop invariants are a very hard problem. And recently, there's been, and there's a really interesting paper from 2013 by Aiken and his co-authors that uses probably approximately correct to make good progress on this. So let's put this aside for a moment, and let's consider simple assertions. So simple assertions are like this one, taken from, forget where I got this. Anyway, some language. It's either JavaScript or Java. And the point is that this is the assert construct. So this isn't a language where we don't have preconditions and postconditions. We just have this assert construct. And just having a code that's annotated with a couple of these allow me to verify some properties of it, at least locally. I can make progress toward validating and verifying that program. The problem is that even for these lightweight applications, and this is even more true for design by contract, is the taxman cometh. So there's the problem of the context switch. If you've actually developed in a design by contract context, it's a different mode of thinking. Wei, do you agree with that? I mean, you're from Bertrand Meyer's group. Yeah, and it's not an easy shift to make, is it? I mean, you're thinking imperatively. You're thinking about the flow of values, and then you think in this declarative, universally quantified in this quantified way.
Certainly need a bit of training, but it is not that difficult. Once you're up with the training, it's very natural to write down. At least simple.
So are you denying that there's not? So I claim there's a context switch even when you're highly trained. That it is a different mode of thinking.
It becomes very natural. So you don't do this context switch all the time, and also.
But did you find yourself going in phases between them? Did you spend part of your time writing the code and then focusing on the annotation, or did you oscillate between them?
Well, I find myself writing contract first before program, and I do this even if I program Python and C.
I think it's kind of like
it helps a lot.
If you're used to doing it that way, then it's very natural for you, I guess. If you're not used to it, it's not so easy.
And the text is something that you pay the tax and you get a lot of benefits from.
Right. Yeah.
Debugging becomes much more natural and faster.
But this is almost an ideological debate because even conservatives here in the U.S., they get a lot of benefit. We have public safety, interstate freeways, and so on, but they still don't want to pay tax.
I think we should all, it sounds to me like we would all benefit from this Kool-Aid. We should drink it.
So regardless of how heavy actually the tax is and what the benefits are exactly. So taking Wei's comments into account, I've had a little more. I felt a little bit more fleeced by it, but I haven't spent as much time as you have doing it. Developers don't write annotations that much. They avoid it. They don't do it in practice. They voted with their feet, and they don't use these languages very much. EIFEL's been around for more than 2 decades. And it hasn't had much industrial traction.
Like Mike and his team at UW published a paper, I think, last year or 2 years ago, on studying code contracts being used in open source projects. Indeed, like a lot of those projects actually using code contracts tend to write preconditions, which are, much simpler for you to specify, but still. Post-conditions are very difficult to specify. Our take is that it's, as you hinted on, too complicated to enumerate universal property in the end of the method body. We are pushing on parameter unit testing, basically invented 2005 at Microsoft Research, and naturally supported by PAX, now Powerful View still 2015. That may have some good hope for uptake in industry. So it's kind of like scenario-based specification. It's writing unit tests, but you are writing specifications when you don't even explicitly realize you are writing formal specifications.
So Lin Tan from Waterloo, judging from comments in a bunch of BSD systems, found that there were contracts in the comments, but none of these are executable or immediately checkable, and they're sort of hand wavy, but the developers would write these little preconditions right there in the comments in C programs.
Yep.
But the C-type system's not capable of handling any of that.
Yep. And I worked as a professional developer for 10 years before coming back to academia, and I can attest to, often in comments before functions, you'd see preconditions. That was definitely, so the challenge here, the thing where ML might be able to help us is in suggesting assertions, helping us alleviate the annotation tax. DICON is dynamic. It's been mentioned several times yesterday and today. It's a dynamic invariant detector. It has a universal set of invariants that are invariant templates, and then it invalidates or disproves them at various program points through dynamic executions. But it's invariants. These invariant templates were created by Ernst from first principles, just thinking about it. And it seems to me that we might be able to use machine learning to learn possible invariants that are bespoke or tailored for a particular code base, and have them be ones that are more likely to be interesting. Because the problem with DICON is it finds many vacuous, irrelevant invariants that are true. You just haven't found a run that disproves them, and even if they're irrelevant to the actual behavior of the function. And then another issue is so suggesting what assertions, and then suggesting where to place them. They're in a sense, they're probes. They have overhead. They're probes to the state space. There might be more natural places to put them than others. Places that dominate, that are dominators in the control flow graph, for instance. And those are not obvious to human developers necessarily. They're easy to find using static analysis, but not immediate to humans necessarily.
This is really a place where something that performs well would be automatically better than humans, because humans don't do that well at it.
Right. So,
sorry, can I ask what is dominator in the control flow graph?
it means that all paths to a node in a graph dominates another node if all paths to the descendant node must pass through the dominator.
Okay, thanks.
Okay, so what developers tend to do, especially now in the age of agile, is they write tests. We do have lots of tests, not as many as we'd like, and that's a problem that I'll talk about in a moment. But they do, agile development tenet is you write a test. You write the least amount of code. You write code scaffolding that passes the test or that checks the test, and then you iterate until you reach a fixed point. So there are two. I'm going to talk to you about two lines of work in software engineering that exploit test suites to do something that test suites weren't necessarily designed to do. Test suites are normally designed to for regression testing to prevent. So they give you confidence that you can make changes. You can evolve the code without breaking existing functionality. And these two are automated program repair and software transplantation. So automated program repair, it assumes it requires something that localizes the bug. And what it does is it synthesizes a path. There are many, there's a wide variety of different automated repair techniques that differ in terms of how they synthesize a fix. But the goal is to synthesize a fix that passes the test suite. And their underlying assumption is that a test suite built for a given buggy program variant can validate a patch program. So they're in some sense they're saying that this test case has some inferential power beyond just the version of the program for which it was written. And I have a paper this year on automated software transplantation. And the idea is that you find a donor program and an organ of interest, some code functionality that you want to move. And this organ of interest has different paths to it. In the donor program. And each one of these paths, each vein, is notable in that it builds the program state, a program state, that this organ expects in order to execute properly. So using a test suite that exercises this organ, I can slice out the organ and one of its veins, insert it into a host where it then can be exercised, automating the process of moving functionality from one code base to another. And you don't get this for free. There are three strong assumptions that we make. One is that the developer must give us the organ entry point. The developer must give us an organ test suite. And the developer must also specify an implantation point where the free variables of the organ can be met. And so again, we're using test suites under approximate behavior. And so as with automated program repair, an assumption of the system is that where the test suite is coincidentally allowing us to approximate the behavior better than that it casts some shadow around its under approximation. We're relying on some inferential power here. And the question is, that's not formal. We just built these tools and they work, but we don't understand exactly, what if any, how are we exploiting getting coincidental correctness from these test suites? And the tests are a biased sample of the program's behavior. So a question here is, can we infer a program's intended input distribution? So when a program is actually deployed and in use, it sees inputs that have some probability distribution that are different from those encoded in the test suite, and they're different from, say, uniformly using uniform random testing. And so a question is, can we get at what the field input distribution might be from the text of the code text and from a test suite? So a possible way to accomplish this would be to use techniques from survey weighting. So surveys have the problem that they sample a population and they're not actually doing that uniformly. So so you can weight them to try to correct for non-uniformity in the sampling. And it might be that there's something we can do here to reweight a test suite in order to get it closer to the intended input distribution. Another possible problem related here is although I said that programmers do write, in the era of agile development, developers do write test suites, they still don't write enough of them. It would be nice, it's tedious and difficult, and so it'd be nice if we could help them write test suites. And the problems with writing, it's not a solved problem. If you just randomly sample the input domain of a program, most of your test suites are going to be useless and redundant. And if you find one that's not useless and redundant, you don't know if the output of the program is correct. This is the Oracle problem, and it's often you often see this problem neglected in discussions of automated test generation. So my proposal to the ML community here is this might be a good place for active learning. It might be that we could use an active learning process with the program and query the program's concrete behavior to infer likely correct behavior. Like a question that we could ask is, can variable x be null? And then not only would we have tests, the queries, but we would also have some error bar around a likely possible correct answer. So this technique might help us address the Oracle problem. Okay, I've talked about three.
The previous slides, about 10 years ago, there's a company, Agita One. This is their product, basically inspired by the daikon idea. More or less, they are doing that. Basically, they infer likely invariants, but with a much smaller subset of the invariants normally produced by daikon. They want to deal with usability. And another very important thing, they have in mind that these invariants are not supposed to be comprehensive. They are more like a triggering starting point for encouraging these developers to write more assertions. So there's a lot of human factors into these pictures. I mean, I have this conversation with the co-founders more than 10 years ago.
Are they still around?
It was close to bankruptcy several years back.
And why do you think that is, Tao?
I don't, I mean, it's a long story, okay. We may talk about offline, but I mean, still a good product, okay. And if for more content and look at I think the ISTA 2007, they have a paper on their products and the whole history of about how they push for inferring these kind of invariants and for getting their products, I mean, being used by developers.
I want to pick up and amplify something that Tal said that I hope I made when I was talking about assertions. Any assertions that we get would be better than the current situation. So even if we just get a handful more, that's a handful that we didn't have that we can leverage. Okay. Thank you. By Shaki?
I mean, there is one problem might be in assertion. You have to ensure those assertions are correct. Otherwise, it will have magnified problem. Than without having an assertion. And we did little bit testing. Like because the training set of assertion is so less, and if we, somehow automatically generate assertions gives a lot of false positives. At least at current state,
Right, so that's the challenge that that's the challenge that was implicit to what I was saying, is that we'd have to do it with sufficient accuracy.
And yes, even human written assertions are quite commonly incorrect. So we did a review of 20 years of IFO assertions when there is a dispute of a crash, whether this assertion is wrong or implementation is wrong. It's 50-50. And when it is case that assertion is wrong, the problem is so much harder to fix.
Exactly. I completely, because developers tend to believe on them, and then it becomes more difficult.
And also it's much easier to propagate to other parts of the system because they all rely on this assertion to be true.
Yeah.
So actually one project that Mike Ernst had proposed to me to try to collaborate on, which I hope we'll do someday, but we haven't started, is to read assertions and read the English comment that goes with it, because that's one of the places that typically is more often commented than others, I guess. Yeah. And to actually try to just find if it's actually lined up.
Yeah.
So is the code actually doing what the English says it should be doing? And as we get into the sort of semantic parsing talks, for those of you that don't know what semantic parsing is, you'll see that one hallmark there is doing really compositional, so building up big complex things by putting little pieces of meaning on each of the words. It's very different than a language model or something like that. And that's exactly what you would need to sort of build those more structured assert queries. So it's sort of an interesting place to think about from an NLP side too.
Cool. But do you get enough English text aligned with assertion?
So I haven't actually looked at the data, but the feeling was at least for Java you would, and large repositories, because people tend to do it. But I actually haven't looked at the data, so I don't know. But it was an interesting idea.
Good. Great. So, okay, let's thank Earl. Good. And coming from a machine learning perspective, we have Danny Tarlow from Microsoft Research. So although in a physical sense he's come a very long way to be here, in some sense, in a logical sense, he hasn't really traveled at all. So he did his PhD kind of doing machine learning and computer vision at the University of Toronto, and he's done a kind of really wide range of research, ranging from kind of more methodological work in approximate inference and graphical models, like one paper won a Best Paper Award from this past NIPS. And in addition, I see kind of computer vision and some sports statistics paper. And then today he's going to talk about some really interesting work that he's done on neural language models for source code.
All right, thank you. So thanks for the invitation here. And I guess the message for the talk that I want to give is there's this class of models that we've been using when trying to build language models for code that seem like they strike a really nice balance of being relatively simple. Hopefully that's my hardest task, is to convince you that it is simple, but also useful and flexible, and allowing us to get some of the benefits of neural networks that we heard about yesterday in their power and their flexibility, but also giving us the opportunity to put things that we know about source code into these models. So for example, that there are variables and they have certain scopes and they live for some amount of time, and you have a tree structure. So the plan is to just tell you about this class of models, hopefully in a way that you all agree that they're neat. Right, and I should say this is based on work with Chris Madison, Miltos Salamanis, Sandy Gordon, and Yue. Okay, so the motivation, I think we've talked a lot about this. I just want to reiterate for myself, why is it that we want to build models of source code? I think the general idea is we've heard lots of cases where there's a whole space of programs that meet some requirement, but you'd like to return a natural one. Maybe you're just interested in the probability of code. But sort of my way of thinking about it is anytime that you want to generate code that people are actually going to look at, then you probably care about generating code that's natural and that obeys some conventions that you find in real code. And so we'd like to build models that produce probability distributions of code that are learned from real code. Yeah.
What's encoding source code?
So if you were coming up, so something that people like to do in, say, computer vision is you take an image, you map it to some code. So this is like semantic hashing came up earlier. You have some low-dimensional representation of an image, and then you'd like to map it back to the original image, and so it's this compression technique. And so if you were thinking about, okay, how do I get from my code that I generated back to my source code, then you could imagine a model of source code would be useful here.
It's like an embedding of source code into another space.
I'm saying I think that probabilistic models of source code would be useful in that context, for example. Anywhere that you're sort of outputting code that's natural code. I don't want to spend too much time on it because it won't come up again, but we can talk later. Okay, right. So this is what I said before. The message that I want to convey is when you're trying to build a model of source code, you don't have to choose between what you know and all of the goodness of neural network-like models. Okay, so there's 4 basic ideas that I want to build up from in thinking about modeling code. The first one is going to be very much from natural language processing, looking at parsing what are called history-based models of tree structures. And then I'll talk about the log bilinear neural language models that we heard some about yesterday, applied to code. And then I'll talk about some more code-specific issues. And then finally, I'll show a couple ways that you can flexibly use this framework in other ways. Okay, so let's start with history-based tree models. Just as a starting point, when thinking about modeling code, you have this first decision that you have to make, which is what is the representation? What is the base representation of code? And the 2 popular ones seem to be either you model tokens, so you take this as just a flat file, you have a sequence of tokens that you have from your lexer, and then you want to model this as a sequence. And the other option is to think of code as a tree, so you run it through your parser, and then you can get back an abstract syntax tree, and then what you want to do is generate these. And so I'm very much going for this bottom class. Okay, so we're going to be thinking about generating source code, which is just sort of the leaves. Is what you'll do is you'll generate this tree, and then if you want to read off the sequence of tokens, you can just traverse the leaves of this tree, and that will give you back exactly your source code. Okay, so tree structures and thinking about models of tree structures. This has a long history in natural language processing and thinking about parsing. So something that people think about there is we want to generate, what we'd like to do is we'd like to take a sentence and produce a parse tree, but a way of thinking about this is saying, I'm going to come up with a generative model of parse trees, and then I'm going to observe some data and try to infer what the parse tree was. So we can look to natural language processing for a lot of examples of this. And the key difference here, though, is in source code, it's easier. So we have access to a compiler. We can just run it. We can get back our parse trees. There's no ambiguity in the parses. We know that the parse tree exactly fits our data. So even though we can look to these models, it's actually much simpler to apply them in the source code setting than it is the natural language setting, or at least at learning time. It's easier to learn these things. Okay, so what's kind of the simplest model of tree that we can think of? Let's start with probabilistic context-free grammars. So the way this is going to work is we're going to generate a tree, but we're going to do it one step at a time, where at each step, what we're going to do is we're going to say we're given a parent node in the tree, and we want to generate a tuple of children nodes. Okay, so this is going to be the basic operation that we're working with. Just to set some notation here, we're going to use R to represent the parent node, C to represent the child node. Do I have a pointer? No. And then this R to C is a production. And if you were to try to learn a probabilistic context-free grammar from observing trees in your model, the sort of the maximum likelihood estimate would be this thing on the right, where you look in your data and you say, how many times have I seen a production that had a parent node R and generated a child node C? And then you would normalize that by the number of times you saw any production that started with the parent node R. Okay? And then I'm going to use this notation a lot throughout. So instead of thinking of it as this ratio of counts, I'd like you to think of it as there's some parameter B for each production from R to C. And what we're going to do in order to come up with our probability is just exponentiate this number and then divide by all of the possible children tuples that we might see so that this is a probability. Okay, but it's just, in this case, they're exactly equivalent. Right, so how would this look? If we're trying to generate a syntax tree corresponding to a program, we're going to start with the parent node here. So let's say we happen to just say we want a for statement. Then the first step, we're going to generate a tuple of children. And so this is the nodes below it that we would see inside our compiler. And then what we're going to do is we're going to recurse to the leftmost non-terminal node here, the initialization. We're going to decide it's a single variable declaration. That requires a type, a name, and an initializer. The type is going to be int. The name is going to be I, and on and on and on. And we can generate this tree. Okay? And so, oops. At the end of the day, at the leaves, we've generated the source code. And actually, I've messed up a little detail here because I've dropped a few tokens that should belong in here. But think there should be the tokens corresponding to equals and the semicolon and whatnot, just as additional nodes here. OK. So right, this is all well and good. We can go to data. We can learn these types of models just fine. They don't work particularly well. They're not so much different than n-gram models as far as my experience is concerned. But so the sort of the first neat idea here is if you're thinking about generating a tree, then in natural language processing, I think they call these history-based models. And the idea is what you think about when you're generating this tree is you have a sequence of decisions to make. Okay, so you're sort of traversing this tree that you're creating, and at each point you're making a decision about what is the next tuple of children that I should generate. And the observation here is that it's perfectly fine. It doesn't change anything in this setting in terms of the complexity of learning or anything to say that my decision about what child to generate next is not just going to be a function of what type of parent I had, like it was in the probabilistic context-free grammar, but it can be a function of any of the decisions that I've made in the past. Okay, so when we're coming here, we've generated int I equals 0. Now we're at the left operand, and we're trying to decide what should be the child that we're generating next. What we can do is we can come up with this, I think of it as this big dictionary where we have features and values of what's been done so far. So you can say things like, OK, in the tree, what is the history of ancestors above me? So above left operand is infix expression. That's the first ancestor. And then above that is expression. Above that is for statement. You can also say, let's look at the past. Let's look at the previous tokens. This would be like you would get in an n-gram model. You can say, how deep am I in the tree? You can literally have any function of the previous tree that you've generated so far. And then what you're allowed to do is, before I had this just a single number here in the numerator, so we have this exp here. But what it can be is you can have an arbitrary function of the child tuple, the parent node, and the history that you've seen so far. And you can combine these together to give you a score. So you can think about sort of linear models or other sorts of models. I'll get into more details about this. OK, so now let's add in this neural component or this log bilinear component. So to get here, let's take what I've told you just now and forget about the tree stuff, and let's just go back to modeling sequences. So let's think about what a log bilinear n-gram model would look like. So this is what we heard about yesterday. Hopefully you remember these neural language models, not the recurrent ones, but the ones that came before that. And well, I guess we could start even with an n-gram model. So we're now saying that we're generating a tree, but there's only one parent type in the tree, and that's token. And then the children are just individual tokens of the model. So now we want to decide what should come next below this token. Well, in this history-based model, we can say we just have this dictionary of what the previous tokens are, what the previous n tokens are. And then our function there that's the numerator can be some arbitrary function of this. It could be the n-gram counts, or it could be some sort of embedding-based thing. And so that's what I'm going to tell you about now. So I should have had some things appear. OK, so this is the work that you saw yesterday as well. This is about neural network language models. And if you go to the paper, you'll see a figure that looks like this. It's not too intimidating, I promise. What you have is you have a neural network. At the bottom, what you're going to have is the previous words. So in this case, int I equals, or whatever. And then what you're going to do is you're going to take these words and you're going to map them to a fixed length vector, so a d-dimensional vector of real values that sort of represent the embedding of what this word means. And then what you're going to do is you're going to concatenate the representations from the previous n words together, and that's going to give you this hidden state here. This is going to be followed by a nonlinearity, like you find in a neural network, a hyperbolic tangent here. And then there's going to be a matrix U that transforms the hidden state to be the size of your output vocabulary, so of something that gives you a score for all possible tokens that you might have in your model. Okay, so then this is your Y here at the top. It's a big vector of length the size of your vocabulary. Then you're going to normalize this to be a probability distribution, and that's going to give you your predictive distribution. Hopefully this is just slightly different notation for what we heard about yesterday. But what you can do is you can think about this in exactly the equation that I showed you before. At the end of the day, there's this normalization over the words in your vocabulary, where the probability of the ith word is some function of I and the history that you've seen so far. And the history that you've seen so far involves, there's also these parameters about all of these embeddings. And the actual equation looks something like this. And I think it's worth looking at this a little more carefully. So right here, if you just had this first term, the bi, then you would get back what I showed you for the probabilistic context-free grammar. So this is just a parameter for each token that says how probable is it. It's like a unigram probability. And then what you can think about here is you have a sum over the previous n words, where you have a representation for the previous word. This is v. This is a vector of length d, interproducted with these uij vectors. And so these are going to be vectors of the same length d. And the inner product tells you something about the compatibility of a word with an output vocabulary word. So there's two different representations of words here. There's one, the v's, which are the representation of input words, and then the u's, which are representations of output words. Both of them are d-dimensional vectors. And then the score that you get in the numerator of this probability term is just a sum of inner products of the output representation for the different positions with the input representation of the word that appeared in that previous position. Are there any questions at this point? Okay. I was going to, I'll show you this just to, well, yeah, I think this is fine. Let's look a little more carefully about where that,
So when you're doing these, are you abstracting the variable names and stuff in some way? Or like when you say I, is it actually I, or is it?
Yeah, I mean literally sort of each distinct string representation of a token is a different word in the vocabulary here. Right, so we can look at this a little bit more. Let's just look at what's happening. This is just to convince you of what I said in the last slide. You have these concatenated input word vectors here, and then you're going to multiply this by a big matrix U. What you can do is you can say, I have a matrix that's of size 1 by 3D, where D is the size of my representation. You can break apart this matrix multiplication to be a sum of 3 terms. It's a sort of, this is just the formula for matrix multiplication. And then you can say the ith term is just by taking an individual column of each of these U matrices. And so don't worry about the details, but this is just a sort of a proof that what you get back at the end is just this sum of input word representations inner product with the output word representation, where you get a different output word representation for each position of the word that you come across. Okay. Right, and then the learning problem, which I won't talk about more, is going to be to learn what these representation vectors are. And you can follow all the standard stuff we heard about yesterday to do this. Okay, so the reason why I've gone into all of this detail is now I want to tweak it slightly. But the key point to take away here is you have sort of an input word representation and an output word representation that changes based on the position, and then you're going to take sums of inner products, and that's going to give you back these scores, which get turned into probabilities. So now let's look at these log bilinear language models that came up in machine learning, natural language processing. So this is from Nguyen and Jeff Hinton in 2007. And what they say is they kind of do away with this neural network interpretation, but they just write down what this score function is here. So this is a slightly different version of what we saw before, but it has the same general flavor. What you have now is you just have one representation vector for each word, the v's here. And then to compute a score for output word I, it's going to be the word representation for word I, inner product with the sum of the word representations for all of the previous words that you've seen. But now what there is there's these K matrices, which they call context matrices, which say you're going to transform a word representation based on a position-dependent matrix. And so there's a word representation that's shared across all of the previous words, but it's going to get transformed by a different matrix based on which position it appeared in. Okay, and then you're going to sum all of these up. You're going to get a score here. And then if you look at sort of further papers along here, there's little tweaks that happen to this model. What happens in this 2012 paper, it's almost the same form, but now you have, again, a different output representation for a word as an input representation for a word. And these context matrices have changed from being full matrices to just being diagonal matrices. And so you can think of that then as an element-wise product of some context matrix, which is just a diagonal matrix. And then you get back something that looks like this. Seeing a lot of blank stares here. Okay. Yeah?
Can you just clarify what the output actually is?
Yes. Well, so what we're trying to always compute is this probability of I, and it's always going to be defined in terms of this score function, which says, in this case, we're just dealing with words. So I is indexing over words in your vocabulary. So what you're getting back is a probability distribution over the words in your vocabulary. It's saying that you're given some previous words from j equals 1 to n. These are your n previous words. And then what you're getting back is a probability distribution over what the next word is.
So how many outputs for the neural net in this case?
So the output is going to be one of these probabilities for each word in your vocabulary.
Okay, so if in this case it would be 3, or?
No, this would be, this is analogous to a 3-gram model. So you're taking in the 3 previous words, but your vocabulary size would be 100,000 or 200,000. And so you would get back, you would take in 3 elements of your vocabulary. You would output a distribution over 100,000 words that come next.
So the I is like one of your output units. So you'll have, so that F is just
for
the
every
equation.
single word in your distribution, you're outputting 1 probability.
Yeah. Okay. So the F is like what's it, proportional to one of the probabilities.
So the number of outputs of the system is the size of your vocabulary.
Yes.
Yeah. Any other questions? Okay, right. And so then we can look at results of how these things work in just the text natural language setting. We heard about perplexities before. This is a measure of how uncertain the system is about what words come next. And what you see here is these are sort of sort of strong n-gram baselines with the Knesser-Ney smoothing. And you can see basically that these log bilinear models, the takeaway is that you can use a larger context size. And so you can go back 10 words here, which you couldn't do with an n-gram model. And then you get back perplexities that are much lower than n-gram models. And then you can do other things, like you can mix this model with an n-gram model, and you can get back even better perplexities. So this seems to be sort of a strict improvement over n-gram models, at least as far as I've seen the latest results in the literature. OK, so then how do we apply this idea to code? And this is kind of where I wanted to get at. So let's go back to having these history-based models. And what we have now is we have this dictionary of features and values from the program, or from the decisions that we've made so far in generating one of these abstract syntax trees. Now what we're outputting, just to be clear here, is a probability distribution over children given a current. So we're given a current node R in the tree. We're trying to expand it and say, let's give us a distribution over the children. So if this is an internal node in the tree, then it might be sort of a list of different node types, or a list of different sequences of node types. And if it was almost a leaf in a tree, then it would be a distribution over tokens in here. So you would have a very large number of possible children. And so the idea here is we're going to have an output representation for the parent-to-child production. We're going to have an input representation for each value that appears in our dictionary here. And then we're going to have a context matrix, or a diagonal context matrix, for each key that appears in this dictionary. So what you can see here is, for example, different internal nodes will appear in different ancestry positions inside history dictionaries at different points in time. The values will always get the same representation across the positions, but they'll be modulated based on how far up in the ancestry they appear. And then the same thing for the history in terms of tokens that have been generated so far. So you have a sort of a subsumption of an n-gram log bilinear model here as well by including these things in the dictionary. Okay, and then this follows the same pattern where you get a distribution over children. Yeah.
Children for a given non-terminal is defined by the non-terminal? Because you're not predicting the number of children here anywhere, right?
So the distribution is over children tuples. And we...
Is that number bounded? I mean, I could imagine for a flat statement or whatever, you could have just a bunch of...
Yeah, so what we actually do here is we say that the support of these distributions comes from what we see in the training data. And then we have to, what we're actually going to do at the end of the day is more complicated, where we sort of combine this model with the probabilistic context-free grammar that gives support to everything. So we make sure we're sort of kosher, but there's a lot of details there.
In some cases, you could have as many children as you like if it's a compound statement.
Yeah. So you could imagine sort of transforming the AST a bit to say, if I have a block, then I have statement and next statement, and it sort of comes out into a fern or something.
I mean, I guess you could use this in a more Markovized type fashion where you do generate one child at a time.
Yeah. Yeah. So we've kind of used the ASTs relatively unchanged in this work, but there's nothing specific to. You could apply some transformation to your ASTs and then apply the model to the transformed ASTs just fine. Yeah.
But sometimes when you generate one next token in the AST, maybe it doesn't make sense.
Sure. So this definitely will give probability to some things that don't make sense. And that's just, yeah, it's an imperfect model for sure. OK. I want to show you some results here. Somebody asked earlier about how sort of neural models compare to n-gram style models on code. So we took the caveat here is it's a relatively small data set. We just pulled it from online. It's about 140,000 lines of C# code. But so we've trained some n-gram models. These now are log probabilities, so higher is better. Apologies for switching that up. But what you can see is really the 2-gram model does best. The 3-gram model is about the same in terms of the validation and test scores over there. For us, a probabilistic context-free grammar worked better than n-gram models. Our models, for reasons I won't go into, we call LTT, and this empty set just means that our history dictionaries were empty at every point in time, and so then it falls back to a probabilistic context-free grammar. We get the same results here. We also trained a log bilinear n-gram model of context length 10, the one that worked best in the previous natural language thing that I showed you. And this works better than the n-gram models, but not significantly better for our results. And then what we did is we said, OK, let's add different types of features into our history dictionaries. So features based on the hierarchy that we've seen before. So what's the parent sequence of nodes that come above the current node in the tree. And then there's also sequence-based features, which are sort of like n-gram-based features. And so what we find is the sequence-based features are more valuable than the hierarchy-based features, but when we combine them, we get something that's better than both. Yeah?
Can you go back? So here, the features, I expect that you would have many cases where you would have a probability of zero because it's very specific. You have many different features.
The features all just get mapped to representation vectors.
Penny, could you repeat the question?
Oh, sorry, yeah. The question was, if features are infrequent, will you get zero probabilities? Yeah. No, so if we've never seen a feature before, we can just give it a representation vector that's all zeros. And that will just not affect this F score. It won't zero out any probabilities in terms of the output distribution. It will just say, I'm not affecting the output distribution.
You don't use any probability distribution transfer, probability mass transfer as you just presented yesterday?
No, there's no sort of... Sorry. OK, you don't use any probability transfer, as Ashish was talking about before. So I think you're talking about the smoothing in the n-gram-based models. Yeah, so this is in the category of the neural network-based models, and so the smoothing is built in, if I can steal a phrase from yesterday. Yeah. OK, let me just, I want to talk about one more little bit, and then I'll wrap up there. OK, so that's sort of a generic tree-based model, and now I wanted to talk about incorporating even more structure about source code and this idea about variables, which are declared, and then they stay in scope for some amount of time, and then they go out of scope. So what we do here is we say, if you look at a tree that you've generated so far, then there are rules in the programming language that just tell you when you've declared variables, right? So we can recognize patterns, or we can just ask the compiler to do it for us, so that at any point in a program, or any point at which we've generated a partial tree, because we're generating sort of in forward to back fashion, modulo things like if you declare instance variables in a class below the current method that you're trying to generate, then we aren't capturing proper scoping rules. But for the most part, we know when variables are declared and what variables are in scope at any point in this process. And so we'd like to use that knowledge when defining this probability over what we're going to see. So what we're going to do is we're going to maintain an extra set of dictionaries where each dictionary is going to represent a variable. And so the variable is going to have features like what is the name of the variable, what is the type of the variable, when was the variable last used, how long ago was the variable declared. We can come up with a lot of features of a variable for any point in the program. And so we're going to have the set gamma that contains dictionaries where each element of each dictionary represents a different variable. And now what we're going to do is we're going to make a slight modification to the abstract syntax trees, where instead of just having identifier token nodes, we're going to have some that we call local and some that we call global. The global is kind of our catch-all fallback for when we don't know what's going on. The local is we're going to generate an identifier that we know is currently in scope that comes from our set. So how are we going to do that? Well, I've already told you how to take a dictionary and turn it into a representation vector. And we're going to do the same thing. So previously I told you about this. We have this history dictionary where we have keys and values, and then we take the value representations modulated by the context representation for the key. We're going to do exactly the same thing, but now for keys and values in the variable dictionary. So we're going to have some representation vector for type int, some representation vector for the identifier name as I, etc. for all of that. And then we're going to combine those together to get a representation for the variable. Okay? And then we're going to combine that together in the same way as before. This sort of used to be just a representation vector for the string I or the token I, but now it's going to be composed of a sum of the component parts of what's made up the dictionary. And then what we can do is we can say that the probability comes from the score for an individual dictionary here, normalized by the probability that we generated any other variable from this set. Okay. Right, and then so how does this work? This turns out to give us a really big gain. So this was what I showed you before, where we incorporated the hierarchy and the sequence features. And this is where we now have this model of scope. I've additionally broken down these log probabilities. You can attribute this sort of cost in log probability to, was it spent generating a tree, or was it spent generating the internal nodes of the tree, or was it spent generating the leaves corresponding to the tokens? And what you see is that by incorporating the scope model, we actually pay a little bit of additional cost in generating the tree, but we get a huge win in terms of the cost of generating tokens. This is kind of what you would expect, in that you can imagine if you know what variables are in scope, it becomes much easier to generate variable names inside your code model. So just to show you samples from this model of what it looks like. So what we've done here is we've said, OK, imagine in the previous line you declared this array of strings called words. This gets put into scope. And now we'd like the model to generate for loops. And this gives you, I think, a reasonable sense of what comes out of this model. It's sort of on the surface not bad, but there's definitely cases where it's generating meaningless code. You can see, it's generating I equals I there. There are certain things where the types don't make sense. Again, it's doing words I is equal to words I. It's having this meaningless statements and whatnot. But syntactically, it's actually quite good. So relative to other things we saw in the development of this string of models, this is sort of far better than we've seen. OK, so I think I'll just wrap up there. The last point is just you can adapt this to other settings. And so we've used this to build joint models of natural language in source code, basically just by adding additional features into the history dictionaries. And then other people like Charles and them have used similar types of models in this class name prediction problem. And so there's quite a lot of flexibility here. So I think maybe I'll just stop there.
So yeah, please.
I don't yet completely understand how many visible units and hidden units you have in your model.
Danny?
Yeah. How many hidden and visible units are there in the model? Keep raising the hand. So the picture to keep in mind is something like this one. If you want to think of it as a neural network, you can, but and if you do think of it as a neural network, then it's just a one hidden layer neural network. So there's this hidden layer, which is like it's roughly going to be like a sum of these different elements here, and then there's going to be an output matrix there. So it's roughly something like a d-dimensional hidden layer, an output that's the size of the number of children that you might see underneath a node in the tree.
The input is a number of features, right?
The input here, yeah, there'll be sort of one block of inputs for each key value pair in your dictionary.
As far as bilinear models, could you please comment on how good they would actually operate on predicting tokens that you haven't seen in your corpus?
So they don't do anything about predicting novel tokens that you've seen before. So one of the details here is we assume that we know what all of the tokens are in the test set up front for all of these models. So n-gram models have the same issue. If you want to do smoothing, you have to know what the set of possible tokens are. And so this is sort of an assumption that unless you're doing subword models of tokens, you're not going to have, you're going to have to make this assumption.
And when you predict new variables, do you have like just opaque name, or you're actually predicting from the space of new variables you've never seen before? Like when you prepare a declaration or whatever, where you don't expect it to be scope yet.
For a variable declaration, we just predict the string. So we just give it a name there, and then the logic kicks in of you've declared a variable with this name.
I guess, could you say a bit about the model with the natural language? Because that's cool.
Sure. Okay, so I took a figure from Miltos' website. He's quite good at doing this. So for the natural language component, think exactly the same model, but now what we have is we have this additional input, which is something like a query that somebody has issued on a search engine. So read file to string. And then our model is going to be of the same log bilinear form. So S, now I've changed notation on you. This is what F was before. It's going to be composed of basically 4 different terms. So this B should look familiar before. This was just the bias, the published context-free grammar term. The R is the representation of the children tuple. This again is the same as before. The C is again the same as before, a combination of the history and the ancestry and whatnot. And then the new thing is we have this representation of the natural language. And we want this to modulate the context somehow. So the model is this diamond is either a addition or a multiplication. It turns out there's reasons to prefer the multiplication over the two. So over the addition, you can see the paper, there's an example for something you can do with multiplication that you can't do with addition. And then, then the basic idea was we went to Stack Overflow and we got a lot of examples of natural language that came from the titles of Stack Overflow questions, and then code snippets that came from answers. And then we trained one of these models. So let's see, the sort of the types of data sets we looked at were, again, we just used C# code. But we have 30,000 questions and 40,000 snippets in the answers. And then what we also did is we went to, sort of being at Microsoft, we went to Bing, and we found search engine queries where people clicked on a page that was one of the Stack Overflow questions with the answers. And so in this way, we were able to associate search queries in natural language with code snippets. And so we have this data set with many more natural language queries, but the same number of snippets. And then, I don't have the results here, but we used these models after they were trained up for both retrieving code given natural language and retrieving natural language given code.
So in this case, you use the same model with the same training for both applications?
So the question is, you use the same model with the same training for both applications, and yeah. So we use the sort of the noise contrastive estimation stuff mentioned yesterday, and the training is actually not that hard. It sort of isn't any harder than other log bilinear models. Yep.
Is that data set available?
No. So I think the Bing stuff will be very hard to release. I think the titles and the questions of the Stack Overflow should be reasonable. I think it was relatively simple just searching against the Stack Overflow dump.
Yeah, do you think it is possible to incorporate character level modeling to a framework, or can we benefit from that?
Yeah, that's a good question. So can you incorporate character level models into into this framework? Yeah, I don't see why not. I mean, if you go back sort of, what we're really doing is, you can think of this as some context representation of what we have so far, and then this is a representation of sort of the word or the token that you're trying to generate. It's just as easy to think of this as sort of a context input into some character level recurrent neural network, and then sort of nothing fundamental would change about this framework.
So can the model be used to like capture, for example, well-typed Haskell programs for this?
Can it be used, sorry?
Yeah, can the model be like used to capture the set of well-typed Haskell programs, let's say? Or
yeah, so can it be?
Or Java programs, right?
Or Java programs, or C or C++.
Yeah, so I think a really interesting question is, to what extent can you guarantee that you're generating valid programs from these types of models? And I think you can get most of the way there. There are a lot of edge cases that concern me. So this issue I talked about before of how do you know which variables are in scope? Well, at least in C#, when you have class declarations, you can declare variables later down in the source file, and they will be in scope inside a particular method. And then there's questions of, if I start generating a method call, am I always going to be able to fill in valid arguments, or can I only generate this method call given certain conditions of the context so far? And in different languages, I think these concerns might be different. So I'm not sure to what extent it's possible to generate all correct programs with some probability and never generate an incorrect program. I think that's a sort of a good challenge for this line of work, though. One in the back, right?
Is it possible to say one day, like, I can give you a corpus of all programs that guarantee that do not give reference null pointers, for instance, and then you learn, and then you train a model on that, and then I use that as a null checker?
You could try. So the question is, can you give it a corpus of all programs that do not dereference null pointers and use it as a checker? I mean, this connects to a lot of the discussions we've heard about, is buggy code unnatural in some way? As kind of, it seems to me, a rephrasing of that question. And so, there's probably some mileage to be had. I probably wouldn't do it that way if I was really security concerned, but.
I have an input. Like in our paper, we found a security vulnerability using natural language modeling. So where the norms were, whenever you are creating a directory, you are always checking directory whether you have permission to create the directory. But so that is your training model, right? And when in one cases they were missing that check, we could figure out that was a security. Yeah.
Take maybe one more question.
So I have a question. So in my earlier study, I saw, the way software changes, that is also very repetitive. So not only like writing the same code, so because we are in an evolving software the way. So I am wondering whether we can predict a model that how software changes.
Yeah, it's a good question. So the question is, can you use similar models for how software changes rather than just generating it from scratch? Yeah, I mean, again, sort of in principle, I see no reason why you couldn't do something like this. So, you could imagine that your sort of side input is not a natural language specification, but it's some representation of the code base that you have already. I'm not sure exactly how I would sort of generate where I'm sticking in code, but sort of in principle, you could say condition on some code that I already have, and now generate some code sort of in context based on that. But I think the details would take some work to get right.
Great. So I think we have a coffee break scheduled for now or something. So yeah. So let's thank Danny again.